Welcome to Study Loop.
Hi, everybody. So, we need to determine the two possible rates of steady position corresponding to 535. Okay, so we have phi, we have x, we have z. We have this little arrow here. We have w capital phi. And the little thing looks like this. Looks like a chew toy, actually. And we have theta, which is what we're looking for. And there we go. And from here, we have RV. And to that W, it's C sine. And let me write that a little bit better. So we have C sine theta. And right here, we have RH. Okay. Now, I think we have enough of the diagram. So we have to express the angular velocity of the system. So we have the angular velocity of x, I hat, plus y, the angular velocity of y, j hat, plus the z component, which is k hat. So we have velocity, and so we can substitute the rectangular component of the rate of the precision acting in the x direction, and the z direction is phi sine theta and phi sine cosine. So what we can do is substitute into this equation. We have phi sine theta I hat plus, and we don't have a y direction, you can obviously tell from the picture, so we can just exit that out, plus the big phi, which we have right here, and we can put that little dot above it, plus theta phi times cosine theta k hat. Okay, and now we need to express the angular momentum about 0.0, which is right here, the initial. So that is just going to be h equals I w x I hat plus I y, and this is plus I y w y j hat plus I w k z k hat. Okay, and here the momentum about 0. O is h0, moment of inertia. And again, this is going to be 0 as we had before. And what we're going to do is have it here and substitute in I here, and we substitute the phi sine theta plus I z k. And we've got the I here. Okay, so, and we're just going to put this as 1, 2, and now we got to expressing the velocity of the reference frame. And what we can do, and so we have this right here, and that equals phi sine theta I plus phi cosine theta k. And what we can do is express this as xyz plus phi times ho. And as we scroll down, so now what we do is have angular momentum as a reference frame is 0 since there is no change in angular velocity. So we have to substitute equation 2. And what we're doing is substituting this one into this one. And what we have is equals 0 plus phi sine theta I plus phi cosine theta k times I theta sine plus I zk. In the matrix location for the cross, so we just do the cross product here. As you see, the cross product. And I said times, I apologize for that. Sometimes I just say it because it gets confusing. That's why when you do multiplication for physics, always just have it like this. Or don't add this into it and say that's multiplication, because it gets confusing, especially when you add cross product into the equations in mathematics. Just a little tip here. So over here we're just going to do the cross product, and we get sine cosine theta minus I z sine theta phi j. And let's make sure I put all the hats on, right? Yes. Okay, so the expression express the moment about 0. So we have MO equals WC sine theta j. And okay, so now what we got to do is plug in equation 4 and 5 into each other. So we're going to plug in, and this will be 4, and this is 5. Okay, so we're going to plug these two together into each other. And when we do that, we have negative WC sine theta j equals I phi sine, oops, there we go. I knew I was forgetting something over there. Cosine theta minus I, and let me try to get this as neat as possible for everybody. Okay, there we go. And it looks like what cancels here is the sine, and the j component. So we have WC equals I phi cosine theta minus I z theta. And now we have C equals I z minus I theta cosine phi cosine theta phi. Okay. And now we're going to substitute in the WZ. So let me write what it is going to be. So we have C equals I, and what we're going to substitute is phi cosine theta plus the large phi, okay, minus I phi cosine theta phi. Okay, and what we're going to do is just simplify this a little bit, and we have here cosine theta plus I phi minus I. Oops, I wrote that phi really weird. Cosine theta phi. Okay, and we're going to just keep going, and we have capital I minus I phi cosine theta phi. And we're going to say this is equation 7. Okay, and so we got to calculate the weight, and you can just use mg. And so we have mass is given as 85 grams, and we're going to times that to get to 1 kilogram. So we have 1,000 grams. Oops, I know this bugs some people if I don't have a consistent. There we go. 9.81 meters per second squared, and we get 0.83385 N. Okay, and we got to express the rate of the spin, which is the big phi, and we have 2 pi N over 60. And the rate of spin that they gave us was 1,800 RPM. So 2 pi 1,800 over 60, and we get 188.496 radians per second. And so now we got to express the moment of inertia about a transverse axis, which is this guy right here. Okay. And we're just going to have it equal to 85 divided by 1,000 to get the kilograms. And when times it by 45 divided by 1,000, because we get 2 meters squared. And here we get 172.125 times 10 to negative 6 kilograms per meter squared. And by the way, using the symbol times is fine when you're doing an answer. Okay, so now we got to find the moment of inertia about the symmetric axis, which is just the normal I, which is mk squared z. And this is, again, just going to be 85 divided by 1,000. And then here it's 21 divided by 1,000 squared. And we get 37.485 times 10 to negative 6 kilograms meter squared. Okay, so now what we can do is substitute all this into our equation 7, which is this. Okay, so what we have is the WC, which is going to be 0.83385 newtons times 0.0375 meters equals, and we're just going to have it here, 37.485 times 10, and this is a normal 37, it's not a negative, there we go, times 10 to negative 6 times 188.496 radians per second minus, and here we're going to have 172.125 times 10 to negative 6 kilogram meters squared, and that's what that unit is too, minus 37.485 times 10 to negative 6 kilograms meters squared, and this whole thing is times by, and this thing is times by phi cosine 30 degrees, which is given to us in the problem, times by phi. And we can simplify, so we have 0.03127 equals 7065.7726 times 10 to negative 6 minus 116.60 times 10 to negative 6. And we have 5. Oops, let me just, and this has phi here, and we have phi here, there we go. And now we have 116.60 times 10 to negative 6 phi squared minus 7.0658 times 10. Let me just rewrite that so you guys can see it better. Times 10 to negative 3 phi plus 31.269 times 10 to negative 3 equals 0. Okay. Looks good. And what we're going to do is a quadratic equation. And that's negative b plus minus b squared minus 4ac divided by 2a. Okay. And from this, we have negative 7.0658 times 10 to negative 3 plus minus 7.0658 times 10 to negative 3 squared minus 4116.60 times 10 to negative 6 times 31.269 times 10 to negative 3, all divided by 2 times 116.6 times 10 to negative 6. And I'm just going to scroll down again. And what we have is we end up with 30.299 plus or minus 5.9499 times 10 to negative 3 times 216.60 times 10 to negative 6. And we have 30.299 plus or minus 25.492. And this gives us 55.791 radians per second, or 4.807 radians per second. Okay. And we're going to scroll down. And so there's two possible states. And what we're going to do is actually times both of these by 1 rev over 2 pi radians times 60 seconds over 1 minute. Okay. And we're just going to times this all by that. And when we do that, we get 532.76 RPM and 45.9 RPM. And that is the answer, guys. Thank you so much.